It's enforced maybe it's better to look at all, but I think it's on. And just one, because it's a computer, we will quickly.
So you can use this laptop. So whenever someone is making noise, you can mute them.
Can I just remove this because it's
Yeah, you can unplug it and use it.
okay. What? Okay. And I just started. Okay. Welcome back to the session of fast implementations for post-quantum crypto. For the first talk, it's online, so it's going to be a video. It's a constant time AVX2 implementation of a variant of Rollo. So it's Tang Chao, Tony, and Yan Han Leo. So, yeah.
Rollo is a code-based scheme that has two implementations of a variant of Rollo, and this is a joint work with Jinghan Liu. Rollo is a code-based scheme that has entered the second round of the Mqpkc competition, and it's a rank matrix scheme. Unfortunately, Rollo didn't enter the third round because of new algebraic attacks. And after that, the Rollo team proposed to use larger parameter sets in order to defend the attacks. But even with the larger parameter sets, actually Rollo still has pretty small public keys, and this is due to the entry-like structure. But unfortunately, there hasn't been much work about how to have a fast constant time software implementation for Rollo, and this is exactly the purpose of our paper. And now I can tell you a little bit about the construction of Rollo. Basically, there's a ring. Well, in the case of Rollo, it's a big field F2 to the NN. And when you write down a big field element or several big field elements, you can consider it as a list of F2 to the M elements. And then you consider the F2 linear space spanned by this F2 to the N elements. This is going to be called the support of the element. And then you can consider rank weight of the element, well, which is just the dimension of the support. And each secret key of Rollo is of the form H0, H1, which has a low rank weight. And the public key is the ratio between H1 and H0. For encapsulation, what you do is that you create low weight elements E0 and E1, and then you compute E0 plus HE1 as the ciphertext. For decapsulation, what you do is that you will first multiply the ciphertext by H0 to form H0, E0, H1, E1, and then somehow by making use of the fact that all the four elements are low rank weight elements, you can make use of Rsr algorithm to compute A0 and E1, or the support of the 0 and E1. And this support will be considered as the section key. Okay, so here are our main optimization techniques. First of all, we improved the Rsr decoding algorithm a little bit, and we call the result Rsr plus algorithm, and we call the resulting crypto system Rollo plus. And we also have some techniques for generating low-weight elements quickly, and also multiply by low-weight elements quickly. And we also figure out some techniques for doing fast constant time Darcy-House algorithm. Darcy-House algorithm is used in Rsr or Rsr plus for computing the intersection of linear spaces. And in order to do this, you have to figure out how to do the Gaussian elimination inside Darcy-House algorithm quickly and constant time, and also how to retrieve the intersection quickly and constant time. And here I should note that the techniques can also can be used for both Rollo plus and Rollo itself. And similar techniques can be used for embedded systems, not only in AVX2. Okay, now on the top you can see the description of the Rsr algorithm. Basically, there are several F2C M elements, F1 to Fd, and also S0 to Sn-1. And the goal is to compute the intersection of Fi inverse big S, where big S is the span of S0 to Sn-1. So what makes this algorithm not so efficient is that in order to represent this space big S, we need n field elements if we don't have any assumption for S0 to Sn-1. But actually we know that for Velic ciphertext, this big S is not going to have rank n, it's going to have some smaller rank dr. So we propose to use Gaussian elimination, to apply Gaussian elimination on S0 to Sn-1 first to check the dimension of the space. If it's the dimension of the space is larger than dr, then we consider the ciphertext invalid. If the dimension is smaller or equal to dr, then we compute the intersection. And this will help you to save the number of rows that you need to represent each Fi inverse big S. Okay, and we also figure out some techniques about dealing with low weight elements. For example, we figure out that each low weight element in F2CNN can be represented as this form, alpha 1, beta 1 to plus alpha 2, beta 2 until alpha d plus d, beta d, where each alpha I is an F2CN element and each beta I is an F2CM element. And this helps us to generate the low weight elements quickly. For example, when we want to generate a low weight element, we simply generate this alpha I and beta i's, and then we apply Gaussian elimination on alpha i's and beta i's to check whether the rank is correct. And we also use this representation of low-weight elements to do multiplications with low-weight elements quickly. So for example, when you want to multiply a generic field element with some low-weight element, what we do is that we represent the generic element as a list of f to the m elements. And then you can multiply the generic field element by all these beta i's very easily. And of course, we still have to deal with these alpha i's, which are in f to the n. And in this case, what you can do is to just do a transpose, matrix transpose, to convert the big field element into a list of f to the n elements. And then you will be able to multiply by alpha i's very easily. And doing matrix transposition is actually very efficient in software. Okay, and as I mentioned before, inside this Rsr algorithm and Rsr plus algorithm, we often want to compute the intersection of several linear spaces. And the Zassenhaus algorithm is a pretty good way to do this. For example, if you want to compute the intersection of of row space U and row space V, what you can do is that you first put U and V like this to form the matrix Z, and then you reduce, you try to row reduce Z to form like this, and then a bit magically, your intersection will be just the row space of this matrix V. But how can we how can we write a constant time implementation for Zassenhaus algorithm? This is not so trivial if you really consider it. So basically, Gaussian elimination has to be constant time, and also this extraction of B has to be constant time. Okay, here's how you can do Gaussian elimination in software. So basically, you consider your input matrix as a mu times a mu matrix in F2, and every time you want to find a pivot P, what you do is that you compute the logical OR of the P's row to the mu's row. And by finding the first index j that's non-zero in this vector v, you will be able to figure out the column index of your pivots. And then here you can see step 4. So step 4 is for basically putting the pivot into the right row. So this process can be represented as a list of logical operations, as you see. And here step 5 is just for eliminating the matrix elements above and also below the pivots. So here the problem is that if you want to find the index j of the first non-zero entry of the vector v, well, this is if you do it wrongly, it can be non-constant time, so you need to take care of that. And also when you access matrix elements using this index j, because j is the dependent of the matrix entries, so you also need to avoid just accessing the elements using memory operations. And today I'm not going to talk a lot about how we do this in detail, but we make use of some intrinsics, AVX2 intrinsics, like move max and permute intrinsics to do this operations in constant time. So after the Gaussian elimination, we still have to somehow retrieve the intersection. And here we consider the matrix as two parts, ZL and ZR, and we also divide the matrix into the upper part and the lower part, each having delta rows. And then what we do is that we run a loop for I from 1 to delta. And for each I, the thing we do is that we check if DL I is non-zero and DLI plus delta is 0. If so, we set DRI to DRI plus delta. Another thing we do is that we check whether DLI is non-zero and whether DLI plus delta is also non-zero. If so, we set DRI to 0. It might be hard to see the effect of doing this loop, but actually the picture here is showing the effect for one case. For example, if you have the case where B has some part in the upper part of the matrix and some part in the lower part of the matrix, the result of this is that the lower part will be brought to the top of the matrix. And then you can use the whole upper right part of the big matrix for your next call of Dawson-House algorithm. And finally, I would like to show some performance numbers. These are numbers for measure on Skylake and Coffee Lake. As you can see, the first big row is showing numbers for previous paper that implemented Rollo 1. And you can see that our numbers, even for the numbers for the level 5 parameters, these numbers are still much better than the previous paper. Okay, and this is essentially all my talk. And I'm willing to take any question if you have any. So yeah, basically that's all. Thank you very much.
Do we have any questions for Tom? Oh, there is one there. Could you just remove the mask and talk? So the question is if there is the artifacts, so the code is public.
That's a good question. Can you hear me?
Yeah, we hear you.
Okay, yeah. So yeah, at this moment the code hasn't been put online yet, but the our goal is to submit to Supercop eventually. Yeah, but well, this is not done yet. But if anyone want to access the code, you can just write an email to us, and then we'll just send it to you. Yeah.
Okay. Do we have any other question? Okay. So since we had a small problem, and it's like we are going to go to the next talk. Thank you, Tony. Let's just say thank you again, Tony.
Thank you.
So for the next talk, we are going to have also AVX, so efficient implementations of UOV and Rainbow using AVX2. And Nahum is going to give the talk.
Thank you for introduction. In this talk, I introduce two efficient implementation method of Rainbow and UOB using AVX2. This is outline out of my talk. First, I give some preliminaries on Mqpkc, and next, I introduce our implementation results, which do not apply our method. Next, I introduce our efficient implementation method of UOB and Rainbow, including block matrix inversion and pre-computation. Finally, I conclude my talk. For key generation of Mqpkc, let F be an easily immutable quadratic map and S and T are immutable affine maps. Then P, which is computed by S circle F circle T, is the Pauli map, and F, S, T are cyclic maps. To generate a signature for given message M and hash value H, commit S using this equation. Then S is a valid signature for message M. To verify a signature S is a valid signature, we compute H prime like this. If H equals to H prime, it is a valid signature. We call these variables by vinegar variables and these variables by oil variables. And we denote V by the number of vinegar variables and O by the number of oil variables, which are equal to the number of equations in central map F. And N, which is equals to V plus O, is the number of variables in F. Then each component function f bracket k of F is of this form. It looks like a general quadratic polynomial, but there's no quadratic terms in all variable times all the variable. If we want to invert F, choose vinegar variables and random and substitute them into each F bracket K, then red parts are converted to constants in this polynomial. No.
Other microphone from other room.
Sorry. So because there are no, I guess
Not these.
sorry. Because there are no quadratic terms with oil variables in each F bracket K, so this polynomial replaces to a linear equation with oil variables. So we get a linear system of all equations with all oil variables which can be easily solvable in high probability. But this system is not solvable, then choose another vinegar variables and try again. U of E is an example of MQ signature scheme using OV map as a central map. Here, unbalanced means V is larger than O. Rainbow is a multi-layered U of E and is a finalist of this PQC standardization. Recently, Brilliance proposed a simple attack on Rainbow so that an equivalent key of Rainbow with security level 1 can be recovered in 53 hours by a laptop. Because of this attack, Rainbow team announced that they replaced the security level 1 parameters with security level 3 parameters and security level 3 parameters with security level 5 parameters. So for UOB, recently, Brilliance proposed the intersection attack, which is suitable when V is less than 2 times O. As a result, in some past parameters, for example, this parameter for security level 1 are vulnerable under this attack. So we suggested new UV parameter considering the complexity of the intersection attack. Very recently, the Rainbow team collaborated with Brilliance, suggested new UV parameters after the simple attack had been proposed. Note that their parameters are slightly different from our parameters. For Rainbow, our implementation of Rainbow is based on source code of Rainbow team, which are submitted in list PQC standardization. So our parameters in our paper is same with these parameters, but we apply parameter changes mentioned in above slide. So the following table describes our parameters. Note that we select Q equal to 256 for all our parameters. Similar with Rainbow, we apply T as this form for U of E, not a general affine map. Each result of our result, each result in this table is an average of 10,000 measurements for each function under this implementation environment. Our implementation results on signing process is dominated by mostly dominated by these two parts: vinegar value substitutions and computation of LSV inverse. So we substitute vinegar vectors into the central polynomial, and then we need to compute the coefficient matrix LSV and constant term of the linear system, which we will obtain. And next, we require to compute the inverse matrix of this coefficient matrix. So our key idea is like this. First one is the Bloch matrix inversion. We can replace an inversion of M by M matrix into two inversions of M over 2 times M over 2 matrix when M is even. Then, and the other one is pre-computation. These two parts can be pre-computed and hence can be omitted in actual signing. First one is block matrix inversion. We write R by this blockwise matrix, where A, B, C, and D are block matrix, diagonal matrices of same size. If A is non-singular, then R is invertible if and only if this matrix is invertible, and R inverse can be written of this form. If D is non-singular, then R is invertible if and only if this matrix is invertible, and R inverse is expressed like this. So computing this value requires two inversions and two matrix multiplication of half-sized block matrices and four block matrix vector product where when K is even and alpha is given like this. The key idea of proof is that we using the LDU decomposition of R of this form, then R inverse is expressed like this. An inversion of M by M matrix can be replaced by two inversions of M over 2 times M over 2 matrices. In a similar manner, each of two inversions of M over 2 times M over 2 matrices can be replaced by two inversions of M over 4 by M over 4 matrices if M is a multiple of 4. If we write K by 2 to the L times K prime, where L is a positive integer and K prime is an odd integer, we can apply the BMI L times. We call this L by a depth of BMI. We cannot expect that L iterations will always be effective because 2 to the L inversions of this size of matrices are required. This table describes the implementation results of BMI on matrix size of this size. We can see that the larger the size, the greater the performance improvement. Especially excellent improvement in the case of 64 and 96 are due to the fact that the multiples of 32 are optimal parameters. Sorry. Optimal parameters which are suitable for the AP2 X2 factorization. If you want to apply BMI to UOB and rainbow signing, we write LSV, which is the coefficient matrix of linear system from the linear vector substitution. We write LSV of like this blockwise matrix and apply the BMI on this blockwise matrix. If A or this matrix is not immutable, then choose another vinegar values and try again. But these matrices are immutable in high probability. This table describes our implementation results on BMI method. Compared to UOB implemented in Gaussian elimination by using the BMI with depth 1, we can obtain speed of this ratio at 3 categories respectively. Next, I introduce our pre-computation method. The general idea of using an offline and online phase was first introduced in this paper. In online phase of signing of UOV, substitute SV, a randomly chosen vinegar vector, into all equations F bracket K, then we get a linear system of coefficient matrix LSV of all equations with all variables. Then we compute the inverse of LSV. If it is not invertible, then go back to the first step. Then this tuple is the pre-computed value. In online phase of UOB, for randomly chosen sort R and hash value H, using this pre-computed value, compute alpha like this, and we compute sigma like this, then this is a signature for message M. Offline phase of first layer of rainbow is similar with UOB, but some vinegar variables, from these vinegar variables of the second layer, which are actually oil variables in first layer, are determined depending on a hash message H. So pre-computation in the second layer is limited, and only the following values are pre-computable. So the following table describes our implementation results on using pre-computation. This row describes signing without pre-computation, and this row describes signing with pre-computation. You can see that there are significant improvement. It's clear that pre-computed values should be stored securely. If it is not stored securely, then we show that the secret key of UOV is completely recovered in polynomial time. And pre-computed value should not be reused in signing. If it is reused, we can recover an equivalent key in polynomial time with high probability. We presented two efficient implementation methods to improve signing of UOB and rainbow, and we gave some implementation results on our method. First one is using the block matrix inversion, which improves the process to solving the linear system. And the other one is pre-computation, which improves the process of substituting vinegar values and solving the obtained linear system. Thank you for your attention.
Thank you. Okay, it's working. Thank you. Do we have questions? Okay, so while people set up, do we have questions here? Okay, I go until.
So thank you for the talk. Could I inquire whether the pre-computation, so how does this work if you run into a singular set of equations? Is it likely to lead to something like a side channel?
Sorry. Let's go again, please.
I guess I didn't. I guess he didn't hear me. So, I mean, when you pre-compute, I mean, it's for a specific set of vinegars, right? So, is it possible to leak any information as a result of like your computation ending up with a singular set of equations?
Singular set.
I think that you can discuss with we in like offline because we have a short time.
Yes.
So thank you again for the presentation. Let's just thank. And then we are to the next talk, which is polynomial multiplication on embedded vector architectures. And it's going to be Hanno that's going to give the talk. So do you use this to play? Yeah. How do you have this? You can play, but you're going to talk with the.
Just to talk to that one.
Or do we want this?
It's about.
Okay. Do you want to see presenter's note?
What does it mean? Just this is.
Okay. Just
Yeah.
Thank you.
Okay, wonderful. Thanks everyone for still being here. So I'm going to talk about polynomial multiplication on embedded vector architectures, this joint work with my colleague Joseph from ARM and Jose Angstrom and Ingrid from COSIC. So first, some words on motivation and context. The talk is primarily about the M-profile vector extension MVE or Helium, which is a SIMD extension for embedded microcontrollers, which has been implemented on M55 and M85 so far. And the research question we want to start is quite simple. We want to understand to what extent we can leverage MVE to speed up implementations of post-quantum crypto. And to just make it concrete, we focus first on Tooncook and NTT-based implementations of Saber on Cortex M55. But I note that the methods we apply do apply more generally. So the agenda is I'm going to say a little bit about SIMD in general and MVE in particular. We look at the algorithmic improvements that we found for Tooncook and the NTT.
We have to stop. Let's share the other screen.
Here, you can see.
No.
Thank you. Okay, and finally, we look at our implementation and the performance results that we obtain. So let's recall what SIMD actually is. So the idea of SIMD is to add a set of very large registers that you can view as vectors of elements of a fixed length. So a vector of length 128 bits, a register of that length you can view as the length 8 vector of 16-bit elements or length 4 vector of 32-bit elements. And then you have instructions like vadd or vmal, which operate usually on those lanes independently. And hence the name single instruction multiple data SIMD. And the first two talks we have seen, they're focused on AVX2, which is one example of a SIMD extension for x86. And in the ARM world, we have Neon, we have SVE, SVE2. This is for the A profile spectrum. And this talk is about MVE, which is for the M profile spectrum. So what are the design considerations going into SIMD on microcontrollers? Yeah, we want to leverage the performance promise of SIMD, but taking into account the tight power and area constraints that we have on microcontrollers. And what do we want concretely? Say if our baseline is the Cortex M4, we would like to have at least 4x speed up for typical signal processing applications. So at first you might think, why can't we just add neon? So why can't we do what we did on the A profile? But if you think about it for a moment, it's not at all clear that this makes any sense, because it's kind of a high performance feature with high requirements that you try to fit on an embedded microcontroller. And to make it even more concrete, for a 4x speed up, say, compared to Cortex-M4, we would need at least 128-bit vectors. But at the same time, we don't want to force any CPU implementing Helium to have, say, 4 32-bit ALUs or a 128-bit data path to memory. That would be too much to ask. And also, if you look at the number of registers, it's too much. We can't ask for, say, 32 registers as we have it in Neon. And the focus that MVE chooses is to emphasize better usage of resources rather than necessarily scaling the amount of hardware that you have. And we are going to see multiple examples for this. And the prime one is instruction overlapping. So in MVE, you have instructions, vector instructions, which can run for multiple cycles, but they are architecturally allowed to overlap. So what this means is that if you look at the architecture specification of MVE, a typical MVE instruction is broken into 4 steps called beats. And the CPU implementing MVE can execute 1, 2, or 4 beats per cycle. M55, for example, executes 2 beats per cycle. And then the architecture says that the last 2 beats of an instruction, they can overlap with the first 2 beats of the next instruction. They can, they don't have to. It usually depends on what execution resources they rely on. And 2 things are noteworthy here. This is architectural overlapping, which saves the microcontroller the cost of maintaining an illusion of atomicity. So if an exception handler hits, this can be in the middle of an instruction. That's okay. And also note that instruction overlapping is not the same as dual issuing. We still only issue 1 instruction per cycle. An example will hopefully make this very clear. Let's say we have a 64-bit data path, and so a 128-bit load would take 2 cycles. And let's say we have 2 32-bit ALUs. So vector arithmetic would take 2 cycles. But arithmetic and load stores, they can overlap because they run on different units. Then we can achieve something as you see in this picture, where you have an alternation of loads and multiply accumulates, each of which takes 2 cycles, but they overlap by half, and therefore you still reach an instruction per cycle ratio of 1. And if you look at it, you realize if you compare this with the Cortex-M4, this scenario here, we have doubled the resources, twice the data path, twice the amount of ALUs, but we get 4 times the speed up simply because we made better use of it. And this idea of instruction overlapping has profound implications on how you design the architecture. So if you look at the specification of MVE, you will find that an instruction is typically designed to describe 128 bits of work in an intuitive sense. So if you look at Neon, you have complex instructions like VLD4, which operate on 512 bits. You don't see this in MVE. It's usually explicitly broken down in multiple instructions, which do 128 bits of work at a time. And they usually operate from low to high bits. That's why you have some certain asymmetry in the instructions that you find. You'll find a long left shift, but you won't find a long right shift, for example. Yeah, but as a programmer, why should I know about this? The main thing really to take away, if you ever consider coding with MVE, and I hope you do, the main rule is, oops, something went wrong. The main rule is that you should interleave different kinds of operations, because that's the way you have a chance to leverage this instruction overlapping. Whereas if you block operations of the same kind, then they won't overlap because they rely on the same execution resource. And very concretely, if you code for M55, you can roughly think of 3 execution units for load store, for addition and logical operation, and for multiplication. So if you look at snippets as you see it here, on the left, this is very bad. It's a nonsensical code, but it proves the point, I hope. You see additions, multiplies, and loads, and they are blocked together. This will be very, very poor. Whereas on the right, you see it reordered in such a way that you never have 2 instructions of the same kind back to back. And this will work well. So you can already see that If you code in assembly, it can be a bit of an effort, but usually it works. And the second point where you make better use of existing resources is about the size of the vector file. You have 8 vector registers compared to 32 in Neon. That's not very much, you might say, but you have scalar vector instructions where you have vector and general purpose register arguments, and that allows you to balance things and make do with just 8 vector registers. Yeah. So next we switch gears. We just look at some algorithmic improvements that we found for Saber. As you probably know, Saber relies on some cyclotomic polynomial arithmetic where the coefficients have precision less than 16-bit. And there are 2 primary means apart from just the plain schoolbook multiplication by which you can implement such a convolution of polynomials. And that's Thun-Cook-Karatsuba and the number theoretic transform. And both have in common that they are examples of multiplication by evaluation, which means that if you want to multiply 2 polynomials, you both evaluate them at a fixed set of points, you multiply those evaluations, and then you interpolate back the product. That's the blueprint that they both use, but the choice of points, the number of points, that's different. And you see some implications of what's good and bad about NTT versus Thun-Cook in this table. And I want to highlight the 2 bad things about Thun-Cook, which is that you evaluate on more points than the degree of your polynomial. So the size of your data expands as you do this. But also if you do the base multiplication, the multiplication of those evaluations, they are doubling the size of the polynomials you still have. Whereas in the NTT-based approach, the number of points is the degree, and you go down to scalars and there's no expansion. So that's really the main difference. But what I want to show you now is that you can at least tweak, get rid of one of those no's on the Thun-Cook column. And for that, let's recall what we usually do in Thun-Cook or Karatsuba. We take a polynomial and we split it in even in low and high half. Or for Thun-4, for example, you would split it in consecutive quarters. But you observe that even if the original polynomial lives in some cyclotomic polynomial rings, if you multiply, you won't increase the size because there's a wraparound. Those smaller polynomials, they won't see this quotient. If you multiply those smaller polynomials, they will double in size. And only as you fold them together in the end, you see the relation. And that's the trouble with the normal Thun-Cook approach. But you can quite easily get rid of this by instead splitting in even and odd parts, or for Thun-4 splitting according to the index mod 4. And if you do this and you think a little bit, you will realize that if the original multiplication is a cyclotomic one, then the multiplication for those subpolynomials is also cyclotomic. So you get rid of this size expansion during multiplication. So the table we get is slightly better for Thun-Cook. We have a green on the lower right. And the motivation for us was to understand how do they compare with NTT after this improvement. For the NTT itself, we also made some improvements. You know that the NTT heavily relies on modular multiplication with constants, which is typically done by 3 multiplications and an addition or subtraction. And for SIMD, it's important that those multiplications are either high or low multiplications, but they are never double with multiplications, which helps the implementation in SIMD. Now here, you could take this and implement it as is in MVE. There's a high multiply, there's a low multiply, but it wouldn't work well because the high multiply only works vector-vector, which would force you to put twiddles in a vector and data in a vector. And with 8 vector registers, you wouldn't get very far. What we do instead is we use a slight variant, the doubling high multiply from fixed point arithmetic, which allows a scalar vector version. And then you can put all the twiddles in general purpose registers and all the data in vectors. And then you can actually make do with 8 vectors, 16 GPRs, you get somewhere. Oops, let me go back. And also, if you look at this blueprint, you might wonder, can we somehow merge the 3rd and 4th step? We do a multiplication and an addition. Isn't there always something like a multiply accumulate?
And if you try this with the addition in the last step and you merge this into the high multiply, it's actually functionally wrong because you miss a carry between low and high part. But what we observed was that you can somehow hack around a little bit by expressing this carry from low to high as a rounding contribution. And there are instructions which do rounding multiplies. And this actually allows you to get a 3-instruction Montgomery multiplication, which is a little bit hacky, and it relies on the constant being odd, which you can enforce. But it works. And tomorrow in the Neon talk, I'm going to present an alternative, which is called Barrett multiplication and also has 3 instructions. Okie doke. So as far as the results go, our development setup is as follows. We had a functional model for the M55 that you can download freely, but that doesn't give you any cycle accurate measurements, but allows you to do functional development. And as a benchmarking environment, we have an MPS3 FPGA prototyping board on which you can put an FPGA image for M55. And this image is free. And you might be interested to know that M85, the newest core, also has an FPGA image for MPS3, which will be released soon. So it's not a super cheap piece of equipment, this MPS3, but it might be worth it. Okay, now there's just one slide on the results, so let's take a little bit of time to digest this. What you can see in this table are performance numbers and cycles for matrix vector multiplication as you encounter it in Sabre. And you have columns for NTT and you have columns for the striding Toom-Cook. And we compare our M55 implementation to a previous implementation on Cortex-M4. So what we see for NTT is that we get a speed of around 3.5x, which now somehow, if you see just the speed up number, maybe it doesn't mean very much, but let's put it into context. We have 128-bit vectors. We are operating on 32-bit data. It's theoretically impossible to get more than 4x speed up. So if we get 3.5, we were quite happy with that. And what it means in terms of this instruction overlapping is that the NTT is a beautiful algorithm also for the purpose of instruction overlapping, because it has a nice mix of addition, logic, addition, multiply, and load store. But if you can't, you have to interleave multiple butterflies, otherwise you have somehow a load bottleneck and a store bottleneck at the top and end. So you need to fiddle a little bit to interleave everything nicely. For Toom-Cook Karatsuba, we get around 5 to 5.5x speed up. So why does that make sense? It's 16-bit data we are operating on, so shouldn't we get 8x ideally? And that's not the case because the Cortex-M4 implementation, which is our baseline, also has 32-bit SIMD instructions which are used here. But there aren't, so you should rather expect 4x, and we get 5x because there are more flexible vector instructions on M55 than on M4. So in terms of the theoretical limits, I think what we achieved, we were certainly happy with that. If we then compare Toom-Cook and NTT, what we see is that even though the speed up is higher for Toom-Cook, NTT remains considerably faster. Okay, so some conclusions. We've talked about MVE. It's a SIMD extension for microcontrollers with 128-bit vectors, which is feasible only because it offloads some complexity from the hardware onto the programmer, such as fewer vector registers, multi-cycle instructions, but they can overlap. So writing good helium code isn't exactly trivial. You need some practice, but what we do show is that for the workloads of interest, it's always possible to write things in a way that really leverages this instruction overlapping. An outlook, this reshuffling of Neon code, you might think that should be automated. And I've worked on a super optimizer for helium assembly, which uses SAT solving to automate the process of ideal register allocation and instruction ordering. So you give it just some readable functional piece like the bad one we had in the beginning, and then it will automatically turn it into a good one. And that's going to be open source soon. In terms of other post-quantum crypto schemes, work on Kyber and dilithium has started, but there's nothing to show yet. So it's a little bit in a limbo state. And all code is available on the PQMX repository. It wasn't very clever to just have this link, but if you open it, you can click on it. Yeah, and there are also some resources at the end, but I'm not going through them. It's just for you if you want to see a bit more. And with that, I'm concluding.
Thank you. Do we have questions? It seems that everyone, oh, there is one there.
You're exactly right. So the interpolation step for Mqpkc is faster because the data you're operating on is half the size. Because it hasn't doubled during the base multiplication. I didn't point that out, yeah. And also algorithmically, what you need, the way you fold things back together in the interpolation step is different than it would be in the normal splitting. But yeah, the main reason why you think it's better is that the interpolation should be twice as fast.
We have one more question or comment. So, okay, let's just thank you, Hanno, again. So for the last talk, it's going to be online. So, I mean, it's going to be a recording, and it's the improved planta arithmetic for lattice-based cryptography. And we are going to see the recording from June Ao.
Hello everyone, now I will introduce our paper, Improved Planta Arithmetic for Lattice-Based Cryptography. My name is Junhao Huang. This is a joint work with Qipeng Zhang, Haosong Zhao, Zhe Liu, Weicixi Chen, Setting Kayakok, and Donglong Chen. I will introduce this paper in 5 parts. First, the introductions. This paper focuses on 2 lattice-based schemes, Kyber and NDTRU. As we all know that Kyber is one of the third-round KM finalists, and according to the latest news, it is also the final KM scheme to be standardized. Kyber is based on the modular learning with error problems, which introduce a small k-dimensional matrix to provide different security levels, while the order n and the modulus q are fixed. NTTRU is an entity-friendly variant of intro KM scheme proposed in TGS 2019. And the parameter, it only provides one set of parameters. And the design of Kyber and NTTRU enable us to implement the polynomial multiplication over these 2 polynomial rings with the 16-bit entity. An entity can factorize these polynomial rings into the product of many small degree polynomials. And the core operation of entity is the butterfly unit, where CT and GS butterflies are 2 commonly used butterfly units. And we can see that during each butterfly unit, the most time-consuming operation is the modular multiplication by the twiddle factor, where the twiddle factor is a well-known constant. And to efficiently implement the modular multiplication by the tutor factors, the state-of-the-art method is the Montgomery or parallel arithmetic. And we can see from these two algorithms that both of them need 3 multiplications. And besides, they both use the product C equal to A times B twice. And thanks to the many years development of the cryptography community, both of them support sign input in a large domain. Therefore, enables the lazy reduction strategy and further improve the efficiency of entity and invert entity. And recently, Thomas Planter proposed a novel Wolfram modular multiplication, which we call Planter multiplication here. And we can see that the biggest advantage of the Planter multiplication is that it only uses the product A times B once. Therefore, when multiplying a constant, for example, B is a constant, the Planter multiplication can save 1 multiplication by computing BQ prime mod to the power of 2L. And therefore, it is suggested that the efficient Planter multiplication by a constant can be used to accelerate the butterfly unit. And however, the original Planter multiplication only supports unsigned integers in a small domain, 0 to Q. This would require an extra addition by a multiple of Q during each butterfly unit. And besides, it may also require expensive modular reduction after each layer of butterflies. Therefore, this disadvantage make the original Planter multiplication impractical in LBC schemes. So this paper tried to investigate how we can efficiently apply the Planter arithmetic in LBC. We now show how we improve the Planter arithmetic tailored for LBC. So the improved Planter multiplication is based on 2 observations. The first one is that the original modular restriction is Q is more than 2 to the power of L divided by 5, where 5 is the golden ratio. On the other hand, the modular in LBC are much smaller. For example, the 12-bit and 13-bit and modulus in Kuiper and NTTRU. So based on these 2 observations, we put a stricter modular restriction over Q by introducing a small integer alpha, where alpha is bigger or equal to 0. And the new modular restriction is Q is more than 2 to the power of L minus alpha minus 1. After that, we observe that the correctness of the original Planter multiplication is based on that this equation is bigger than 0 and smaller than 2 to the power of 2L. And we modify the original equation into a new equations. And we also show that this new equation is also bigger than 0 and smaller than 2 to the power of 2L for AB in this domain. So based on these 2 tricks, we present an improved Planter multiplication, which is shown in algorithm 4. So this algorithm supports signed integers AB in a large domain under the new modular restrictions, and also produce a signed output R in this domain. And as for the main step, we only need to multiply the +1 to +2 to the power of alpha. And we prove that the algorithm 4 is correct under the new restrictions. So compared to the original Planter multiplication, the improved Planter multiplication supports signed input and produce signed output. And besides, we also managed to extend the input range from 0 to Q up to a large domain, which eliminates the final correction step in the original version. And besides, the improved Planter arithmetic also have some merits over the state-of-the-art modular arithmetic. First, in terms of efficiency, the Planter arithmetic can save 1 multiplication when multiplying a constant. And besides, the parallel arithmetic may require an expressive strip operation for a non-Wolfram offset on counter sample, which may further slow down its efficiency. And as for the input range, plantar reduction accept input in a large domain, which is about 2 to the power of alpha times bigger than Montgomery reductions. And finally, the output range of the improved algorithm is half of the Montgomery's. So with all these advantages, the improved plantar motivation also have some merit weak spots. First, the plantar arithmetic introduced a special L times 2L bit modifications, and we show that it is suitable on Condensate 4, M7, and some 32-bit microcontrollers when L is equal to 16. And second, the compute triple factors are double-sized compared to the implementation with Montgomery arithmetic. It requires extra cycles to load the triple factors, but we show that by combining with the layer merging strategy, these extra cycles can be covered. And we now show how to integrate the improved plantar arithmetic into Kyber and NTTIU. So the target platform of this paper is the Condensate 4, which is a NIST reference platform. And it has some SIMD extensions, which enable us to perform addition, subtraction, or to pack 16-bit vectors in one instructions. And the most important instruction we use in this paper is the SMOD WB or T instructions, which can efficiently compute the 16 times 32-bit modification in plantar arithmetic. And modification instructions are normally 1 cycles, while the load or store instructions are relatively expensive. So we need to reduce the use of a load and store instruction as many as possible. And in the following section, we set L equal to 16 to suppose the 16-bit entity in Kyber and NTTIU, where alpha is equal to 3 or 2 in Kyber or NTTIU, such that Q satisfies these new modular restrictions. And based on the improved plantar arithmetic, we present an efficient 2-cycle plantar modification by a constant, as shown in algorithm 5. In this algorithm, we assume that B is a constant, so that we can pre-compute B with Q inversion mod to the power of 2L, so that BQ prime is an 2L bit integers. After that, the L times 2L bit multiplication A times BQ prime can be implemented in one instructions as mod WB. And the follow-up operation can be implemented also in one multiplication instructions. And compared to the state-of-the-art Montgomery implementation on Condensate 4 present in TGS 2020, we can save one multiplication, namely 1 cycles on Condensate 4. And as for the modular multiplication of 2 variables, we present 2-cycle plantar reduction, which is as efficient as the state-of-the-art Montgomery reductions. However, it has a larger, bigger input range and smaller output range. And we show that this advantage over Montgomery arithmetic will enable better entity implementations. And as mentioned before, the most time-consuming operation in the butterfly unit is the modular multiplication by the triple factors, where the triple factors is a well-known constant, so that we can utilize the efficient plantar multiplication by a constant to accelerate the butterfly unit. And to do this, we need to first compute the triple factors by first multiplying a plantar constant, so that the plantar multiplication can produce a result in a normal domain. And besides, we also need to multiply it with the Q inversion mod to the power of 12. And the triple factors are double-sized compared to the Montgomery implementations. And in summary, we can implement the true modular multiplication by the triple factors in 4 cycles, in 4 instructions. So compared to the Montgomery-based implementations, we can save 2 cycles for 2 CT butterflies, namely saving 1 cycle for each butterfly unit. And because using the plantar arithmetic introduced the 32-bit triple factors, therefore it requires extra loading cycles to load the triple factors. But we show that by combining with the layer merging strategy, the improvement brought by the Planter arithmetic can cover the side effect of the double-sized trifecta. For example, in the three-layer merging strategy, each iteration of each layer can reduce 8 cycles at a cost of only 0, 1, or 2 extra cycles for loading the trifectas. And because, as introduced before, the input range of the improved Planter reduction is about 2 to the power of alpha times bigger than Montgomery's, while the output range is half of the Montgomery's. And with this advantage over Montgomery's arithmetic, we show that using the Planter arithmetic would enable better lazy reduction strategies and reduce the total number of the modular reduction of coefficients, because using the Planter arithmetic would halve or slow down the growing rate of coefficients. And when the coefficients would overflow the 16-bit sign integers, modular reduction of the 16-bit coefficients are required to reduce the coefficient size. And in this paper, we show that Planter reduction can also be used to accelerate these operations. And the proposed double Planter reduction faster than the state-of-the-art implementations. And as for the result and comparisons, we integrate the improved Planter arithmetic into 2 versions of Kyber implementation. First, the code from Teachers 2020, and then the stack version code from ACNX 2022. And this paper showed that integrating the Planter arithmetic into entity and inverted entity obtain quite good speed up compared to the Montgomery-based implementations, over 20 to 25% speed up for entity and 11 to 20% speed up for inverted entity. And as for NTTRU, to the best of our acknowledgement, this is the first work that presents the assembly implementation of NTTRU on context sample. Therefore, we only compare the reference implementation in Teachers 2019. And thanks to the parallel implementation and the improved Planter arithmetic, the speed up range from 55 to 83%. As for the performance of the overall Kyber schemes, we obtain slight speed up with the same stack usage. And the slight speed up mainly can be explained by the fact that entity has been well optimized, while the symmetric cryptography accounts for a large proportion of cycle counts. And it should be noticed that our implementation based on the stack version code from Teachers ACNX 2022 outperforms the DSP version code with merely half of the stack usage. And as for the NTTRU schemes, we obtain about 50% speed up thanks to the optimized polynomial arithmetic. So in sum, this paper presents an improved Planter arithmetic tailored for LBC, and it has some merits over the original Planter, Montgomery, and Ballard arithmetic. And by replacing the Montgomery and Ballard arithmetic with the improved Planter arithmetic, we obtain speed up for Kyber and NTTRU with 16-bit entity on context sample. And future work can be done on its application on other platforms or on other schemes with 32-bit entity. And it should be noticed that Daichi et al. Present a similar and concurrent work in Arithmetic 2022. They also present a similar sign version Planter arithmetic and apply their sign version arithmetic to Cyber on a 64-bit RISC-V platform, which clearly shows that the potential application of the Planter arithmetic on the schemes with 32-bit entity. And that would be all. Thank you for listening. I would love to take any questions.
So do we have questions? Okay, so no one seems to have questions, but I have a question. Can you hear us?
Yes, yes. Do you hear me?
Yeah, okay. So you presented the 16-bit version and you said that can extend to 32. There is any reason why you didn't go further in the paper? Like why you didn't explain the 32 bits, or it's just
Yes, it is because due to the limit of time, we only focus on one platform, the countersample. And in countersample, the 32-bit entity cannot be well optimized due to the limit of the, we cannot perform the 32-bit times 64-bit multiplication on countersample because it is a 32-bit platform. So we didn't extend it to the 32-bit platform entity.
okay? Thank you.
Yes.
We have one more question.
Thanks for the nice talk. Are you going to merge your code back into PQM4? Have you looked into this?
Yes, we are looking forward to do that. But right now, we are planning to do that in the next few months, and we will. Yes.
Okay, so thank you for the presentation. Thank you. Let's just take everyone in the session.
Thank you.
And it seems that we have announcements. So
No, not really announcement, just to remind you that at 6 we have a dinner again in the place where we had the lunch. And then at 8 we are back here for rump session and open bar. Enjoy.